Hello, in this video we are going to look at a problem involving combinatorics and permutations. Let's look at a famous problem that the answer might surprise you. Imagine a group of people. How big would the group of people have to be so that there is more than 50% chance for two people in the same group to have the same birthday? Assume for the sake of simplicity we'll ignore the leap years and there are no twins in the group. Take a moment to think about it. The answer might surprise you. In a group of 23 people, there is 50.73% chance that two people will share the same birthday. How can this be when there are 365 days in a year? To answer this question, let's start with a simple one. Suppose there are 3 people in a room. What is the probability that there is at least one shared birthday among these 3 people? Remember the rule of subtraction? Probability of A equals to 1 minus probability of A complement. So the probability of at least one shared birthday is equals to 1 minus the probability of no shared birthday among these 3 people. Now, out of 365 choices of days in a year, the first person has 365 possible choices out of 365 days. Then, the second person has 364 possible choices, as one of the days is the birthday of the first person, and the third person has 363 choices out of 365. This is the probability of no shared birthday. And so, to get the probability of at least one birthday, we subtract 1, the probability of no shared, and we get 0.082. Now let's make the group bigger. Suppose there are 5 people in a room. What is the probability that there is at least one shared birthday among these 5 people? Just like the previous one, the probability of no shared is equals to, and we take all those 5 probabilities and we get 0.9729, and when we subtract it by 1, we would get the probability of at least one shared birthday among 5 people would be 0.0271. We can also simplify the equation for the probability of no shared birthday. So let's take the equation from the previous example. Since the denominator is 365 multiplied by the number of people, we can rewrite it as 365 to the power of n. Then we can use factorials to simplify the numerator part. Using factorials, the factorial of 365 would equals to the product of all the descending integers from 365 down to 1. However, we only want the product of the integers from 365 to 361. So, we'll divide out the extraneous numbers by dividing the factorial of 365 with the factorial of 336. Then, to generalize the formula, we will get a formula such as the probability of no shared birthday is equals to the factorial of 365 divided by 365 minus n factorial times 365 to the power of n. Back to the birthday problem, the probability that 23 people has no shared birthday would be the factorial of 365 divided by the factorial of 365 minus n, which is the factorial of 342 times by 365 to the power of 23, which is n, and we will get 0.4927, and after we subtract it by 1, we will get the probability of at least one shared birthday among 23 people would be 50.73%, which is more than half. Now, why is our intuition at guessing the answer in the first place is not reliable? I'm sure most of us, if not everyone, would have guessed a much higher number of people is needed. This is because our brain is really bad at intuitively grasping nonlinear functions. The key to such a high probability of a match is the surprisingly large number of possible pairs. As the group grows, the number of possible combinations would grow much faster. A group of 5 people would have 10 possible pairs. Each of the 5 people can be paired with the other 4 people. Half of the pairs are redundant because comparing person A with person B is the same as comparing person B with person A. So we divide by 2. A group of 10 people would have 45 pairs, and a group of 23 people would have 253 possible pairs. Using the same reason, a group of 70 people would have 2,415 possible pairs, and the probability that two people have the same birthday is more than 99.9%.